Okay guys, I just wanted to quickly discuss checking the assumptions for linear regressions and multiple linear regressions. So you're all well aware of the assumption of linearity, which is basically just the idea that the relationship between each IV with the DV is linear. However, once you start getting to multiple linear regressions, it'll be really time consuming to check the relationship between the IV and the DV for each IV. So instead what we do is we plot the residuals versus the predicted values. So the residuals is just the predicted value minus the actual value for each participant, and you see whether this is linear. So the way in which you do this, basically if it is linear, you expect to have for each value of the predicted value, you expect to have a reasonably equal distribution of residuals. So the residuals cluster around the middle here, and then they spread out a little bit, and it's equal. There's no pattern to the relationship. So what it's showing us is that the scatter of the residuals is there's equal scatter of the residuals for each of the predicted values. So there's no relation, which suggests that the relationship is linear, because if it was non-linear, then you might have, so say it was curvy linear, then if you're using a regression or a correlation, which is testing linear relationships, then you'd end up with larger residuals at some predicted values and smaller residuals at other predicted values. So it wouldn't be a nice even scatter across the predicted values like this. So for example, when you scroll down, here's a non-linear relationship. So you can see that if you graph residuals if you graph the residuals for each predicted value, you have negative residuals here, positive residuals here, and then back to negative residuals, which suggests that the relationship between the IVs and the DV is not linear. There's been a violation of that assumption. Okay, so let's have a quick look now at equality of variances, how to test for equality of variances. So again, we would use a scatter plot, so it's really similar. And again, we're just looking to see that the relationship between, that there's a even spread of residuals for the predicted value. We're looking for that again. Hold on, if I scroll up a bit. So here is what you want. So it's the same, it's pretty similar to the value. I think it's exactly the same graph as what I was showing you before, but you can see here that the spread of the residuals for each value of the predicted is pretty even. Okay, I mean it's not perfect, but it's pretty good. So that suggests that there is equality of variances, whereas here you can see it fans out. They're really thin. The spreading out of the residuals, this looks like a scale, so the values can't, cases can't take any value. It looks like they can take 2, 4, 6, 8 or something like that, or 1, 2, 3, 4, 5, 6 or something like that. So you can see how they're lining up rather than being scattered all over the place like the one above. That suggests that some sort of scale has been used. That's fine, but here you can see that it's really spread out at one end and really thin at another end. So that means that the distribution of the residuals is not equal for each predicted value. So this is the distribution of the residuals for, say, a predicted value of 1, the distribution of the residuals for a predicted value of 2 or something like that, the distribution of the residuals for a predicted value of 11 or 12, all the way up to 30. And you can see that the distribution of the residuals for a predicted value of 30 is much wider than the distribution of the residuals for a predicted value of 10. So that suggests that equality of variance has been violated. There is not, the distribution of the residuals for each of the predicted values is not equivalent. Okay, so that's that assumption. And then, however, if you have a scatter plot like this, this suggests that both linearity and equality of variances has been met, and so you can start testing for normality. Now again, for normality should the assumption is that at each value of the independent variable, the dependent variable must be normally distributed. However, it's really difficult to test the distribution of the dependent variable for each value of the independent variable. In fact, most of the time you're not going to have enough participants. So say you're measuring height and you've got participants range from 15 to 25 years old and you've got 100 participants. You might have 10 participants at each age, 10 who are 15, 10 who are 16, 10 who are 17. And so that's not enough participants to see whether the distribution of height for all of the participants age 15 and the distribution of the height for all of the participants age 16 and the distribution of height for all of the participants age 17. There's not enough. If there's only 10 at each age, there's not enough participants at each age to test to see that the distribution is normal. So instead what we do again is we just test the residuals. So for example, when you run a regression, you can ask in the plots for a normality probability plot and the histogram of the residuals. So this is a histogram of the residuals and this is a normal probability plot of the residuals. So if there is no violation of linearity or equality of variances, then you can test for normality like this. If there is violation of equality of variances, for example, you can't test normality like this because as I was discussing before, when we were looking at equality of variances, the distribution of residuals for each value of the predicted variable of the distribution of the residuals for each of the predicted values is not equal. So you can't just take this mass approach. I mean, one way to get around that might be to test the distribution of the residuals for each predicted value, but as I just discussed, that's not always viable. So what you would do in this situation is actually beyond the scope of this course, so don't worry too much about that. But basically, just remember that you can only test for normality using residuals if linearity and equality of variances have been met. And that's it. There's also additivity, which is reasonably straightforward. Additivity is just basically the idea that there's no interactions between each variable. And so you learnt this week how to test that, and that's just basically you need to multiply the two IVs together and add that multiplication into the regression, and if it's significant then there is an interaction, which means the assumption of additivity has been violated, and if it's not significant then there isn't an interaction, which means the assumption of additivity hasn't been violated. If one of the IVs that you think might be interacting with another IV happens to be dichotomous, then you can split the file and run a regression separately for each of the groups in that IV, and if one of them is significant and the other one is not, then this suggests again that there's an interaction.